other on the circle, let me play with it a little bit. So let me count the number of integer points in such a circle. So draw a circle of radius square root of 11, and I want to find out how many integer points fall inside of this circle. And I have, well, maybe not the best way, but still, the way to actually find the answer. I will count how many Gaussian integers are there from 0, 1, 2, 3, all the way up to 11. So let me try. Number of, so maybe I call this norm and Gaussian integers. Let me make such a table, and I'll just count how many Gaussian integers are there of norms 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's start. How many Gaussian integers are there of norm 0? Just one. How many Gaussian integers are there of norm 1? 4. These are the units. So 4 units. So here we have the answer 4. How many Gaussian integers are there of norm 2? Okay, yes, so 4 is the correct answer. And well, one of the ways is just to think about 2 is the sum of two squares, a squared plus b squared, so both a squared and b squared should be equal to 1. So a and b should be plus minus 1. We have 4 integers. These are the integers. It's 1 plus I, 1 minus I, minus 1 minus I, minus 1 plus I. So 4 Gaussian integers. Or you could apply this formula here. There are no prime factors besides the factor of 2, so there is only one choice, and well, you introduce the units, plus minus 1 plus minus I, so there are 4 choices. 3. What about 3? 0. Because in prime factorization of 3, you have a prime factor which is congruent to 3 modulo 4 to power 1. What power of such factor? So no integers. What about 4? Yes, should be 4. Because once again, it's 2 to some power times nothing. So it's the same situation as this one. Well, what are these 4 numbers? 2, negative 2, 2i, minus 2i. Okay, 5. How many Gaussian integers here? Well, let's look at the formula. 5 is, well, 5 to the power 1. And 5 is 1 modulo 4. So here we have just S1 which is equal to 1. So in this formula we get the answer of 2. And we have the units. So we have 4 choices of units. So 4 times 2 is 8. And once again, it's very easy to understand what are these 8 numbers. If we actually want to write them down, it's plus minus I plus minus 2 and plus minus 1 plus minus 2i. These are the 8 numbers. What about 6? 0. So 6 is 2 times 3. So the prime factor 3 appears to power 1. So 6 is 2 times 3. And because of this 3 to power 1, there are no ways to write it down as a norm of something. So 7, 0. Because 7 is congruent to 3 modulo 4, so no ways to write it. 8 is a power of 2, so the same situation as this 2 or this 4. there are 4 ways. 9. Well, not quite. 9 is 3 squared. So yes, you do have a prime factor which is congruent to 3 modulo 4, but it appears to an even power. So there is a way to split it between z and z conjugate. So there are 4 ways. And well, the actual integers here are 3, minus 3, 3i, and minus 3i. Well, let's continue. More number. 10 and 11. So 10 is 2 times 5. So we do have a prime factor of known 1. So S1 is equal to 1. S1 plus 1 is 2. So it's 8. And finally 11, there are none. Because 11 is 3 modulo 4. So it's 11 to the power 1. This power is 4. So the number of integer points inside of this circle, number circle is 1 plus how many pores do we have? 1, 2, 3, 4, 5. 5 plus 4 plus how many 8s do we have? 1, 2. So it's 20, 36, 37. So using the complicated theorem, we counted the exact number of integer points inside of this circle. And in general, it turns out that the problem of actually counting how many integer points precisely are there in the circle is a complicated one. Nobody knows a short and simple answer. I mean, we have an algorithm how to find it, we have a kind of geometric algorithm how to find it, just draw a big circle and count, but both ways are pretty complicated. There is, however, a very simple way to estimate how many integer points are there. Because look, you have a circle and you have some integer points. Something like this. You can draw this picture on square paper like this. And then with every integer point inside, you have usually a whole square of area 1 inside. Well, with most of them. Except for a couple which are close to the boundary. So for example here, well, it's not really like this. Not the whole circle fits inside. So besides some points here, which are kind of error, let's say it's small error, let's call it small error. Essentially the number of integer points is more or less like the area. So area of this circle pi times r squared, which is in our case pi times 11, because the radius is square root of 11. So a rough estimate of how many integer points are there should be pi times 11. And how good is this estimate? Well, since you do know what pi is, you can decide for yourself. So from here we say that pi times 11 is approximately 37. So this number comes from number theory, from counting actual number of integer points inside the circle, or counting how many Gaussian integers are there from most 11. This number comes from obvious considerations. You look at the circle, you see that usually integer points come with a whole square inside of the circle. Except those which are close to the boundary, but most of the points are not close to the boundary. At least that's what we hope, and that's actually what is true. So we get a way to approximate approximate pi if we want, using this procedure. Count in this arithmetic way how many points are there in a large circle, and divide by radius squared. That's an approximation to pi. Kind of funny thing. Oh, of course, 37 over 11 is not, it's not really close to pi. It's 3.4, but it's also not that far away. So it's not really pi, but if you enlarge the radius, I mean, we took a very small circle. We took a circle of radius square root of 11, which is between 3 and 4. So we've taken really small circle. If you take a circle of radius 100, well, you do get an approximation which is pretty good. So I'm just going to say that it's a funny arithmetic way to count what is pi. Okay, so maybe any questions about this? Okay, so the good news is we covered all the material that is going to appear on the final exam. So Gaussian integers and this last theorem is the last theorem in the material for the course. So from today, from now basically until the end of the course, we are going just to cover some fun topics. Maybe I still have to decide what we are going to cover exactly. But well, whatever comes from now to the end of the semester is not going to appear on the final. Well, if people want to review, I can arrange a review.
First of all, shouldn't we make up the topic for back 9 approximation?
So, no, we won't. I decided that it's, well, I mean, it's much less related to any other courses than the topics which I am going to cover. So.
Okay. But actually, I prefer doing examples. Doing example as we are examining is more instrumental, useful than going over random article.
Okay, so
that's my suggestion.
We'll devote some time to review. Maybe give these examples of questions, maybe hard questions for previous exams or something like this.
Yeah.
But let's not devote all the time to this.
Sure.
Okay, so any other questions? So first thing I want to discuss just a little bit, a tiny bit, is well, what comes after this course. So we covered some very elementary number theory in this course, and well, from here, number theory, well, it does develop. One of the ways it develops is algebraic number theory, which appeared basically out of attempts to solve the following questions. Prove that for any n which is greater than 3, x to the power n plus y to the power n is not equal to the power n for any integers x, y, and z, any natural numbers. So, natural numbers x, y, and z. There is a funny story associated to this problem. Fermat he was a mathematician, and he was thinking about different kinds of riddles, mostly about riddles in number theory, and this was one of his riddles. He wanted to understand when it is possible to write z to the power n as the sum of nth powers of two numbers. And well, he thought that he didn't know a solution, and he wrote that, well, I do know the solution, which the margins of the book on which I'm writing these words are too small to contain. And well, people were fascinated by the fact that well, somebody did know a solution, but somehow look at this question and you don't see a solution. And well, people did figure out, I think, well, most probably what Fermat meant. I mean, well, we don't know for sure, but the most probable way of thinking about this question is something along these lines. We have this equation. If we have z to the power n is x to the power n plus y to the power n, well, we know how to solve this question if this power is equal to 2. And, well, basically, the best way that we did in this course was using Gaussian integers. We joined I, and then we factored the right hand side as x plus iy times x minus iy. It is possible to factor this polynomial in complex numbers as well. So if you take psi to be a number which is nth root of unity, psi is not equal to 1, then this polynomial can be factored as a product of linear polynomials. It turns out to be x plus psi y, x plus psi squared y, times x plus psi to the power n minus 1 y. So there is some complex number such that this equation actually factors in this way. Well, not really unusual natural numbers. This number is not natural number. It is some complex number. So if, well, let's do the same here. Let's take this number psi and write expressions of the following form. So these integers are, well, kind of integers, are expressions of the following form. A0 plus a1 psi plus a2 psi squared plus a n minus 1 psi to n minus 1. And I don't have to continue because psi to power n is already 1. So in such integers, you can multiply stuff, you can add stuff. So this is what's called a ring. You can add stuff and multiply stuff. So if in this ring you do have unique factorization, then you can apply all the tricks that we covered in this course. So if in here there is unique factorization, then if there is a unique factorization, then basically x plus psi to the power of iy, each one of these factors must be x factor of something. Because, well, let's factor this thing is a product of primes in this ring. Let's factor each one of these numbers. It's not hard to show that they're all relatively prime to each other. And then, well, every prime from factorization of this should appear to the power which is divisible by n here. So n is some number to the power n. So basically, it's the same stuff we did with Pythagorean triples can be done with this Fermat question. But only if in this ring there is a unique factorization. Unfortunately, well, there is unique factorization in this ring only when n is equal to 3. And that's it. So n equal to 3 can be solved in this way, and it's not hard. And I'm pretty sure that Fermat did solve this particular case because he has a separate remark about this special case of n equal to 3, and he describes beautiful dissenters procedure. And, well, he does have a separate detailed solution of n equal to 3 case, and probably he thought that it's always true. You can always factor in this way. But unfortunately, it's not true. Ulmer was the first one to understand this, and he tried to understand what can be done when there is no unique factorization, and he came up with what essentially is known as algebraic number theory, which will develop from there. We'll cover more and more stuff, but unfortunately it didn't cover this question. So this question can be solved for many exponents n using what's called algebraic number So algebraic number theory. A large part of it is about the question of what to do when an interesting thing integers doesn't have the factorization. So there are special courses in our department about algebraic number theory, and well, they might not start with this question, but eventually they develop enough theory to cover the answer of this question for some special exponents have. Not all of them, but some of them. And if you want to read about this or a good introduction to this is the book of Cox called Primes of Form S squared plus n y squared. So just very good book to read as an introduction to this topic of algebraic number theory.
But why is called algebraic? I thought purely algebraic rather than.
Well, so there is, you need to distinguish algebraic kind of number theory from what's called analytic number theory. So let me make a short introduction to analytic number theory. I'll cheat a little bit, but don't read it. So today we found a way to write a fine formula. So so that given n, which is of this form, 2 to the power t, we want to power s1 times and so on, k s k times q1 to r1 plus s1 q n by n. So here's a number n. Let me go with the name f of n, this funny number 4 times s1 plus 1 times and so on times s3 plus 1. So given such number n, I can write down this number f of n. Well, it is some function of the number n. What we proved today is that the number of integer points inside of a circle, inside of a disk of radius square root of n, is exactly like this. It's 1 plus sum from n equal to 1 to n f of n. So this is number of integer points in such a disk. On the other hand, we show that approximately this is equal to pi times square root of n squared. Pi times radius squared, which is this number. Oh, so here we have a funny formula. On one hand side we know an approximate value of some basic arithmetic function. It's sum of such functions over all the numbers from 1 to n. On the other hand side, well, it has something to do with factorization of numbers to prime factors. So the basic idea is, well, you know approximately this answer, and you want to understand, for example, how many prime numbers which are equivalent to 1 modulo 4 are there between 1 and big N. Well, one starting point that can help you is, well, start with this kind of formula and try to analyze it and try to understand what information does it give to you about your question. So, once again, sometimes you have the following situation. You have a question, the answer to which is given by some arithmetic function which is very interesting to you, or well, maybe not very interesting, but related to some function which is very interesting to you. On the other hand side, we have other considerations. For example, geometric considerations, which tell you not exactly what is your function, but kind of approximately. Sometimes this is enough to give you interesting answers to interesting arithmetic questions. For example, question of how many primes are there from 1 to n which are congruent to 1 modulo 4. So that's about this question, this problem. So let me give you some interesting answers, and then then tell you a little bit about the most interesting parts. I mean, this is kind of stupid example. I gave it just because we are able to understand it. But so interesting answers in this direction. For example, like this, the number of primes from 1 to n is approximately equal to n over 1. So you can actually find how many primes are there from 1 to n. Well, not exactly. It's n over 1 of n, and the mistake here is the mistake after an error of order n divided by 1 squared. So something like this. And in fact, you can get, well, if you try harder, you can almost prove such a formula. Number of primes from 1 to n is integral from 1 to n dx over 1 of x. It turns out that this formula is much more precise. Plus minus what's called plus a mistake of order square root of n. And these results will they can be proved using this kind of, well, of course not this simple idea, but kind of these considerations. So what happens is the following. There is a funny thing called quadrant product. It looks like this. You take all possible primes and you consider such a product. 1 plus, well, you take the first prime, which is 2, and you consider such a sum. 1 plus p1 to power sum power z plus p1 to power 2z times. Oh, let me first consider kind of simplified version. Still, let me do it. I take such a sum. It's very little idea, but still. 1 plus the second prime to the power 2 plus the power 3 and so on times 4. And you continue. For each prime, you form such a sum, infinite sum, and you multiply all this stuff together. Well, yes, this sum does not converge. Yes, it's really a bad idea to work with such sums, but still, let's do it. Let's kind of open the brackets formally, and let's see what we get. It turns out that what we get is exactly like this. It's 1 plus 2 plus 3 plus 4 plus and so on. Why? Because every number here can be factored in a unique way as a product of primes to some powers. So take any number here, say 12. 12 is equal to 2 squared times 3. Well, here's the prime number 2. It must come as one of the summands in one of the brackets. Well, let's take the bracket which corresponds to 2. It's the first bracket here. And let's find 1 plus 2 plus 2 squared. Here it is. Here's the factor 2 squared. Let's take number 3. The corresponding bracket is the second one here. Let's find the factor which corresponds to 3. Here it is. And essentially, if you open the brackets, there is a unique way to choose the factors from each one of these brackets so that you will get exactly the number that you want to get here. The problem with this is, well, it's really a bad idea to do such a thing. This sums are infinite. I mean, this equality holds formally, but not in any reasonable sense. But you can change it a little bit and raise each one of the primes to some power, z. And then you get such identity. Here it is better. It is actually much better. The reason it is better is because if z is small enough, I mean, say negative 10, then this sum does converge and this product do converge. And even better, each of these products is in fact, well, can be computed. What is the first product? It's sum of arithmetic progression or sum of geometric progression whose term is p1 to power z. So its sum is 1 minus 1 divided by 1 minus p1 to power z power. And on the other hand, this is equal to 1 to power z, sorry, to power z, to power z. 2 to power z, 3 to power z, and so on. So here's equality, precise equality. For well, quite a lot of values of z, it actually does make sense, and this is just equality. On the left-hand side, we have something very interesting about prime numbers, a product of some stuff, which, well, basically here it is something like this, 1 minus 2 to power z, 1 divided by 1 minus 3 to power z, 1 over 1 minus 5 to power z, and so on. So, how large is left-hand side depends on how many prime numbers are there, or, well, it is related to prime numbers somehow. The right-hand side, well, it's just a function. It's sum of powers of 1 to power z, 2 to power z, and so on. You can try to investigate it using usual calculus. Well, it turns out that it's better to use what's known as complex calculus. So if you've taken complex calculus first, then you know that this function will make sense not only for negative reals, it will also make sense for complex numbers whose real part is negative, and small minus 1, I'm sure. But anyway, this function has a sense in complex plane. You can study its properties that you learn how to study in complex analysis, poles, how fast it grows at infinity, at some special points. And this information about this function, basically knowing how to approximate this function near some particular values of z, gives you a lot of information about prime numbers. So that's the idea of analytic numbers. And this, of course, has grown a lot. I mean, this is known as Riemann zeta function, and there is famous hypothesis, Riemann hypothesis, about some special properties of this zeta function. It's not the only interesting function in analytic number theory. There are functions due to Dirichlet, due to Artin, lots and lots of functions. So once again, very interesting topic, and I'm not even sure what book is to begin with. I will ask for the next time. And also let me announce what we are going to do next time. next time we are going to discuss kind of this question. We talked about what would be the last digits of a power of 2. We know some case of how to find the last digits of the power of a number, but what are the current digits? How are they distributed? What can you say about them? 2 to the power of 2 start with 9. And we'll discuss this question and the application of this to changing class effects. Really.